All right, thank you very much. First of all, I would like to thank the organizer for giving me an opportunity to talk. And I also need to kind of apologize a little bit for changing the title, but actually the topic is not really changed. But it's just that I'm going to kind of focus on specific aspects of the correlation function of n equals 4 super mu theory, which is the analysis at strong coupling. So the topic of my talk is, as I said, the correlation function of n equals 4 super mu theory at strong coupling. But let me first give you some motivation of this work. So one of the important features of ADS-CFT correspondence is the emergence of geometry from some quantum mechanics. For example, ADS-CFT itself is the relation between d-dimensional conformal field theory and d+1 dimensional gravity, which is geometrical. And also, inside ADS-CFT, there are many baby versions of this kind of phenomena. For example, the Wilson loop in n equals 4 super mu theory corresponds to some minimal surface. And also, as we all know much about it, entanglement entropy is also related to minimal hypersurface in ADS spacetime. But if you really want to understand how the geometry emerges from the gauge theory or from CFT, and there is some difficulty. And the difficulty is the fact that we need to analyze the strong coupling regime of the conformal field theory or the strong coupling regime of the gauge theory. And even when it is possible, for example, using localization, it is often not so clear what kind of physical or mathematical mechanisms are responsible for the emergence of geometry. And the goal of my talk is to analyze the strong coupling regime of planar n equals 4 super mu theory using integrability. And the punchline is that for the emergence of minimal surface, the mechanism or phenomena which we call clustering of magnons are pretty much important. And also, this clustering of magnon has some resemblance to the mechanism which appears in the analysis of Nekrasov-Shota-Shvili limit of instanton partition functions. And also, there is some relation with the Fermi gas formalism of the ABGM theory. OK, so let me be more specific. So the object I would like to discuss today is the 3-point function. Yeah, in particular, among the correlation function, I would like to discuss the 3-point function. And as we know, since n equals 4 super mu theory is conformal, the 3-point function is completely determined by the space-time dependence of the 3-point function is completely determined by the conformal symmetry, and the non-trivial information is encoded in this C123, which we call structure constants. And if you want to do the analysis at tree level, then the computation is pretty much easy, because what you need to do, especially if you want to study the large n, planar n equals 4 super mu theory, and if you focus on the single trace operators, what you need to do at the tree level is you just need to do that planar weak construction. And for example, if the operator consists of L fields and L1 fields, and operator 2 consists of L2 fields, and operator 3 consists of L3 fields, typical weak construction is of this form, and the number of weak construction between two operators is completely determined by the length of the operator. For example, the number of weak construction between O1 and O3 is given by L3 plus L1 minus L2 over 2. And in the rest of my talk, I will call this number the bridge length, because it's sort of the length of the bridge which connects these two operators. So, and as I said, at weak coupling, the computation is pretty much straightforward. So for example, for instance, if you take operator 1 to be of this form, which is the operator where Z is the complex scalar field in the n equals 4 super mu theory, and a D plus is the covariant derivative along one light-like direction. And if you take O1 to be this kind of non-BPS operator, and O2 to be BPS operator of this shape, and O3 to be a BPS operator of this shape, then it was shown by Viela and Wan that the structure constant have this form, have this structure. So let me explain what this formula is. So first of all, in integrability language, what we do is to map the operator to a spin chain system. And if you do the mapping, then this D plus is the magnon or excitation in the spin chain. And the operator is actually described by the set of the number of magnons and the rapidity, which are moment of magnons. And this formula is given by sum over bipartite partition of the rapidities of the magnon, or rapidities or moment of magnons. And it consists of 3 terms. And first term is a weight factor, which is given by S matrix of the spin chain. But more important are these two last terms, which are denoted by H. And this H is a kind of simple product of the rapidities, which belongs to alpha. And each function H is given by a simple rational function of the rapidities. So this is the structure what you get. The structure you get if you do the honest weak contraction using some spin chain technique. And last year, together with Benjamin Basson and Pedro Vieira, we proposed the generalization of this formula to finite coupling based on using the integrability structure. And remarkably, the conjecture basically takes the same form. And the only difference is that this H of alpha, and also weight factor, but the most important difference is that this H of alpha now takes a little bit more complicated form. And it's given by a little bit more complicated function, where this X of u is what is called Joukowsky variable, which actually encodes the dependence on the coupling constant. So here I'm using kind of convenient way of parameterizing the coupling constant, where lambda is the 2/5 coupling and g is the coupling constant I'm using to define this function. So, and actually this, our conjecture is that this expression is valid as long as the operator or the length of the bridge is sufficiently large. And we are calling this asymptotic part of the structure constant. And behind our proposal, there is actually a very geometrical idea of how to consider the 3-point function. And the idea is to regard the 3-point function as a pair of bands. Because if you consider if you recall the weak contraction at tree level, it has a topology of pair of bands. And then if you have a pair of bands, the idea is to cut it into 2 hexagons. And each piece actually corresponds to the contribution coming from this hexagon. And the important point is that the contribution coming from each hexagon, you can actually determine it by using integrability. And what is nice about this geometric feature is geometric interpretation is that you can also understand the finite size correction, which is the correction to the asymptotic part I just described. And basically, the idea is when you cut the pair of bands into 2, you need to insert the resolution of identity here and here and here, or a complete set of states. So the leading term is just given by the hexagons or asymptotic parts, and the subleading parts are given by some insertion of non-trivial states. And you typically get this kind of integral. And we checked that this expression is actually valid up to 3 loops. So up to 3 loops in the gauge series side, our proposal is tested. On the other hand, a strong coupling, because we believe that there is ADS-CFT correspondence, you can actually compute the structure constant using the minimal surface. And using integrability, one can actually compute the area without knowing the surface. The idea is very similar to the one utilized by Alday and Maltasena for this computation of a scattering amplitude, but the details are a little bit more complicated. But the basic idea is very simple. If you have a 3-point function, then the corresponding worldsheet, if you go to the strong coupling, and then the corresponding worldsheet is a worldsheet with 3 legs, where these 3 legs actually corresponds to the operator inserted at the boundary of ADS. And if you do this computation, then, OK, so if you do this computation, you get some expression. But in order to explain a little bit about expression you get from this computation, I will briefly explain how you characterize the operator, macroscopic string, which corresponds to heavy operators in ADS. In integrability approach, each heavy operator in AD class, which corresponds to macroscopic string, is characterized by some function, P1. Well, actually, I should put some hat here, but P1 of u, which is basically the generating function of classical charges. And this P1 of u typically have several cuts. So regardless of the states you consider, it always have a cuts from -2g to 2g. And in addition to that, you have some extra cuts. And these extra cuts basically characterize the states you want to consider. And the final expression is for the structure constant at strong coupling. is given by well, this is actually a very complicated expression, but what is important is that it's given by some integral of the dilogarithm, and the exponent of the dilogarithm is given by some combination of that quasi-momenta, which we use to describe the operator. And there are actually two different sets of contours, and one is around the cut between -2g to 2g, and the other around different cuts. So my goal today is to reproduce this expression, which comes from the minimal area from the hexagon I just described. And okay, so in order to do that, I will first rewrite the sum over partition expression I just expressed. The idea is to convert this sum over partition into some integral expression. And here, this n is basically the number of elements belonging to alpha bar. So because alpha bar, the number of elements of alpha bar must be 0 from m, where m is the total number of magnon, you have this summation like this. And it is, well, this expression seems a little bit might seem a little bit complicated, but it's actually easy to show that if you take the residue, then you get back to this expression, sum over partition expression. And what is interesting is that because delta of uu is 0, you can actually extend this sum to infinity. And what happens here is that because, so in this expression, there are some poles in the integrand at the position of magnons. But if the integration variable is more than m, then there must be some different integration variable which takes the value which is at the same position of the rapidities. And because of this property, those contribution basically vanishes. So using that property, you can actually extend the sum to infinity. This is just a simple rewriting. But there is actually one nice feature about it. And the reason is that if you go to strong coupling, this interaction part takes a very simple form. And if you use this simple form, then you can actually realize that this is nothing but the determinant. So this is actually the famous Cauchy determinant formula to rewrite this and this. And once you express the structure constant in this way, you realize that the structure constant is the same as the expansion of what's called Fredholm determinant. And what is nice about Fredholm determinants is that if you have a determinant of something, then you can also take the logarithm, and the logarithm also takes a nice expansion because it's a trace of log. And much like, as in the case of Fredholm determinant, it has actually a nice expansion. So if you take the logarithm, then it's given by in over n. So because it's a 1 plus expansion of 1 plus something, you get something like this. And each contribution is of this form. And this integrand is basically has a ring structure. So if it has fz to fzn, and it's connected like this kernel in a ring-like way. And if you have this structure, then the next thing we should ask is what is the strong coupling limit of this expression? So if you want to express or analyze the macroscopic string limit, then what you need to do is to take some scaling limit where the rapidity scale as order g and this function f scale as order 1. And if you take this limit naively, then if you take this limit naively in this expression, then you see that the I1, which is given by this, is order g because you have the integration of z here. So it's order g. But on the other hand, if you consider n where n is larger than 2, then there is some cancellation between these factor and this denominators. So it seems that you get just order 1 contribution. So if this is true, the result is very simple. We just need to take I1 piece in order to compute the leading structure constant at strong coupling. But it turns out this is not really true. And the reason is because of what we call clustering mechanism. So in order to see what the clustering is, it is convenient to first reparameterize this z variable such that z becomes g times z prime. And after this reparameterization, Z prime is just order 1 quantity. And if you do this reparameterization, you get expression like this. Sorry, this has to be prime variables. And if you look at this expression, you see that there is a pole at Z2. For example, if you consider the integration of Z1, then there is a pole at Z2 plus I over G, or Z2 minus, Z2 plus I over Z, or Zn minus I over G. And this pole, if you take the strong coupling limit, this is again wrong, this is infinity, but if you take the strong coupling limit, these poles actually pinch the integration contours. And this kind of phenomena is also observed in the context of n equals instanton partition function of n equals 2 theory, and that was analyzed by these 2 papers. And so the whole point is that the contour get pinched by the poles and each some singular contribution. So the resolution of this problem is to first deform the contour such that they are well separated from each other, and then take the limit afterwards. So let's do this analysis. So let's first consider I2 case. So you have so suppose that you have 2 integration here and this blue one, and what we need to do is to first deform this blue one to this large one, C prime. And if you do so, and you immediately see that there are several different contributions, and one contribution is just the one coming from C prime, but if you analyze this object, then you can basically use the same argument and say that this is just order 1. But on the other hand, there is a contribution coming from the poles here and here. And if you analyze the contribution, for example, from the pole here, then let's see what we should do. So you have this expression, and then you take the pole at Z1 equals Z2 plus I. And after doing so, you get this expression, which is Fz plus 2 plus I and Fz2, and you have some 1 over 2 coming from here, down here. And at strong coupling, this change by I is not relevant, so you can actually approximate this one as Fz squared. So in the end, what you get is this expression, and you can see that this is indeed order G contribution, unlike the naive expectation, because you have just integration over Z2. And you can do the same analysis for IN, and it turns out if you do the analysis for IN, then what you need to do is to take poles subsequentially. Then the result, it turns out that the result is given by this expression. So what is important here is that you have extra 1 over n here. And if you plug in this expression here, then it turns out, because you have 1 over n here, if you multiply 1 over n times 1 over n, you naturally get 1 over n squared. And after doing so, we can actually resum the expression, and you can indeed see the emergence of dilogarithm. So if you do this computation, then it turns out that you can actually reproduce one of the terms which appears in the minimal surface result. But you can see in this expression that there are also other terms which are not accounted for by this expression. But the remaining terms actually come from the finite size corrections, which I didn't explore so far. But the analysis for the finite size correction is very much similar, so I will be very brief about it. So as I said, the finite size correction is given by some kind of integral like this. And especially if you look at the contribution coming from the bottom channel, so the states living here, then if you do the analysis carefully, then it turns out that the bottom contribution actually factorizes. So the final result should be given by this times this. And the rest of the analysis is very similar, but the only difference is that now the integration is, so now we have integration from the beginning. It's from minus infinity to infinity. And another difference is that, this is a bit technical point, but unlike the previous case, there is a kind of flavor sum, which, this A is called bound state index, and we need to kind of sum up all different particles living at the bottom edge. And if you perform this flavor, so you need to perform this flavor sum. Then And if you do this same analysis, then it turns out, in this case, instead of the usual Fredholm determinant, you get some kind of a bit generalized Fredholm determinant, which contains the bound state sum. And actually, a similar object appeared also in the context of Fermi gas analysis. But because although it's a little bit different, but anyway, it's just a Fredholm determinant, we can actually do the same analysis. And as a result, we can actually reproduce the last term of this minimal surface result. So, yeah. So basically, this is the. All right. So I think I still have a lot of time. So now I already got to the conclusion. So what I explained today is how to reproduce some parts of strong coupling answer, minimal surface answer, from the hexagon analysis, from the hexagon conjecture. And what was important in order to reproduce the results of the minimal surface is the phenomena which I call clustering of magnons. And I should mention that the same kind of phenomena is also necessary when you want to study the strong coupling limit of the null polygonal Wilson loop. So in the case of null polygonal Wilson loop, there is a non-perturbative approach, which is called Pentagon OPE program. But also in this case, in that case, the analysis of strong coupling is a little bit more difficult, but it is known that this kind of clustering phenomena is also important there. And you can also see that what I did here is another test of hexagon conjecture. So let me briefly explain the future direction or future prospects. So of course, what is important here is to reproduce the other terms, because so far I just explained how to get this term and this term. But conceptually, there is not so much difficulty, but there are some technical difficulty. And this expression, this term here, is supposed to arise from the left edge, left channel, and this term here is supposed to arise from the right channel of the hexagon, whereas this term is supposed to arise from the interaction of 3 channels. So reproducing the remaining 3 terms is very much important future problem, and we are working in progress. Yeah, we are working in that direction. So, but there are some technical difficulties, but we hope we can overcome very soon. But what is more important is to ask what the physical meaning of this clustering phenomenon, because in my talk I just explained that this is the clustering is an important mathematical mechanism in order to reproduce the minimal area. But in order to really understand the ADS-CFT correspondence, it's important to really understand the physical meaning of this clustering phenomena. And another kind of natural direction is the resummation of the finite size correction at finite coupling, because what I did today is something like resummation at strong coupling, and it might be interesting if there is any relation to thermodynamic beta and that's. But I think what is most important in this research program is to really understand the 4-point function using, for example, OPE or some other methods, and we are working in that direction too. And once we can understand the 4-point function, then we can imagine taking the strong coupling limit again. Then we can ask various interesting questions like the emergence of bulk locality and so on. And we are really kind of hoping to understand the physics by analyzing 4-point functions. So that's it, and thanks very much.
Okay, so we have 6 minutes or so for questions. Any questions? Sure.
A simpler question is just about the strong coupling limit of conformal dimensions,
Yes.
anomalous dimensions.
Okay.
Is that completely understood already?
All right. So yes, Okay. Well, I think there is fair enough understanding right now. So there is a method called like TBA or quantum spectral curve, and if you just focus on the really strong coupling limit, I think people are understanding how the string theory result, classical string theory result, arises from those finite coupling method.
My question is related to the TBA.
Mhm.
Why would you expect it's only happens at finite coupling? Because at strong coupling there is also a Y system combination.
In the case, yeah. Well, okay. So, well, the TBA is all right. So what I meant here is really about finite coupling computation. But of course, there might be some relation already at strong coupling. But in the case of scattering amplitude, TBA arose already at the really strong coupling limit. But in this case, the structure like TBA doesn't arise in the case of three-point function.
So you only have the Lie function.
Yeah, we only have Lie function. So.
Any other question? Have some more time.
You say a few words about the 4-point function?
Okay. All right. So yeah. So there are two possible approaches to 4-point function. One is to use OPE and then compute this 3-point function using our method. And the other is to directly construct the 4-point function. And we are making some progress towards that direction. But if you're interested, I can explain a little bit more about it later.
Okay. The vacuum that you use for this hexagon, is that the BMN vacuum?
It's BMN, yes. It's BMN.
Any other question? Sure.
Is there any generalization for other operator, some light operator? Or
Well, it's an interesting question to ask. So yeah, if you want, for example, if you consider the large spin operator, maybe GKP might be a better description, but we haven't explored much in that direction.
So, sure. Contributively, is there any, for 3-point function, is there any understanding beyond like one loop or is there higher?
Okay, so there are people who are computing 4-point function of BPS operators, and once you have and that is done up to 3 loop. And if you have a 4-point function of BPS operator, then you can OP decompose and read off some of the structure constants.
But do we see like interpolation with a strong coupling calculation?
Interpolation, not really. Maybe the only interpolation I can think of is our formalism, hexagon formalism, because it matches the 3-loop result and also it matches the strong coupling result.
Everybody satisfied? Okay, then let's thank Shota again.
All right, thank you very much.